Let me just start beating you a little bit to make you feel at home. We know each other, right? Okay. Now, of course, as I mentioned to you, these experiments work well when it is dry. And so, if you are too wet, it won't work. But let's see, if you sweat a little bit too much, then it doesn't work too well. So, you ready? I have here in my hand a neon flash tube. And although we don't know yet what voltage is, because we will learn about that in this course, to get a good flash out of this you need about a few thousand volts. And so we will see, and we'll make it dark shortly, and I will hold the flashlight in one hand, the neon discharge tube, and then Simon will touch it on the other side. And if we succeeded, then you may see some light. So, Simon, look at me first. Don't touch it yet, because we're going to make it all the way dark. You know where it is? It's there. Okay, make it dark, Marcos. Touch it. Touch it. Okay, try it again. Touch it again. Okay, thank you. Can we have some light? Thank you very much. Equal charges repel each other. I've shown that, the demonstration with the balloons. Here we have an instrument which is called the Vandegraaff. It's named after Professor Vandegraaff, who invented it. He was an MIT professor. And this instrument, which I will not discuss in any detail now, but you will understand it later on in the course. I'll tell you all about it later. Think of this instrument as a super amber rod. And although we don't know yet what voltage is, I mentioned already the 20,000 volts between Simon and me, in this instrument you have to think in terms of several 100,000 volts. So this instrument is not without danger. But that, of course, makes it more exciting to work with it. So it's a super amber rod. And what I will do first now is to put some confetti on top. And when we turn on the Vandegraaff, the confetti may at first go to the charge dome, it is already on top of it, and when it picks up some of the charge, it will then spread out because it will repel. And so let's get some light on there, which will make it a little bit better to see. Let me put some of this on top. It's just regular confetti, pieces of paper. All right, now all I have to remember is how to start the most of the action has already occurred. I will put a little bit more on. If you see sparks, don't worry yet. Put some more on. Ooh, boy, nothing left for the second class. Make it perhaps a little darker. Ah, that's too dark. Okay, we'll try it once more, give it a zap. So look at the confetti on top. And I think it's quite convincing. Some of the confetti will stay there. Well, that's for reasons that it's not a good conductor. And so it gets first sucked in, and if it doesn't get charge of the Vandegraaff, then it will not spread out. All right. So now, let's try for the first time to be a little bit more quantitative. If I take two charges, and we use in general, we use for charge the symbol Q. So here we have Q1, and here we have Q2, and let's say they are separated by a distance r, and the unit vector in the direction from 1 to 2, I call that r roof 1, 2. The roof stands for unit vector. If these charges are equal, both minus or both plus, then they will repel each other. And so here there is a force, F, which I call 1, 2. This is the force onto due to number 1. And since action equals minus reaction, force here is 2, 1, equal in magnitude, but 180 degrees in opposite direction. Coulomb, a French physicist, who did a lot of research on this in the 18th century actually, Coulomb found the following relationship, that the force is proportional to the product of the two charges. So it's Q1 times Q2 times a constant, which nowadays we call Coulomb's constant, K, divided by the distance between these charges squared. And it is in the direction of the unit vector that goes from 1 to 2. This is the force on number 2 due to 1. And notice that this equation is sign sensitive, because if Q1 and Q2 are both negative, the force is in this direction.